Okay, welcome to Object-Oriented Programming. This is already the 7th time. And yes, what is today's content? Today we'll talk about Smart Pointer. You heard that last time in the lecture. We'll talk about application, and maybe also so you can understand them better, we'll implement some sort of dumb Smart Pointer today. And then afterwards, we'll talk about algorithms and lambda functions.
Yeah, so this is a more advanced topic then, but we think that this is very interesting, so we would like to teach it to you, that you also get some insights there.
Yes, and it could also help you with the homework.
Yeah, with the homework, yes, exactly. But first, of course, there are some organizational matters, as always, so the boring stuff at the beginning. Assignment 1, the grading is still missing. I already have all the grades, I just need to upload them, and I hope that I'm able to do this after the lecture, so in today's evening you should be able to see your grades of A1 latest at some point tomorrow morning. Apart from that, I just want to remember you that next Wednesday there is the A2 deadline, and next Thursday there will not be a lecture because the lecture finishes today, but nevertheless we will do a bit more in the practicals, and this is our most favorite practicals unit because we will do some more topics in C++ which are not part of the exam but which are, we believe, very interesting, and that's why you should come also next week to the practicals.
Yes, and maybe it's also part of the homework.
Yeah, so we will have homework 2 and homework 3 release, and we merge those two homeworks together, that it's just one large homework. And as well as assignment 3 release is next Thursday, but I think this will be done in a separate video as it's for all assignments. And one last thing, then afterwards, we have the assignment interviews for assignment 2. You will get all important information at some point next week, and also the registration in the Teach Center. But just a quick outline, so just maybe open it. Here we have the deadline of A2, and then the week afterwards, the interviews will take place, and we'll extend it a bit because on Thursday there is some holiday. Okay, that was the boring stuff. Now it's your time to shine, and we have a short quiz.
Yes, so the quiz is about smart pointers. So I think this is the first time we decided to do a quiz on the topics of the lecture without doing them in the practicals before.
Yeah, so this is now the test for the exam, whether you have already know everything about smart pointers. How many people do we have today? 30? Maybe? So maybe we start at 20 then. So you need to be fast. Maybe wait till 25.
Okay.
One more.
Now we are like in the lecture. One more.
Yeah, but now we can start.
Okay. So this is the first question.
I might open it somewhere else.
I think it's big enough if you stay in there.
Really? Is it big enough? Okay, it looks good. What happens there? We have a unique pointer which will be initialized with 42. Then we assign it to another unique pointer and print it.
Yes, and print the second one. Okay, we have 9 answers.
Yeah.
Okay, so let's look at the results. Most of you voted for the compile time error. And this is also the correct answer because we have a unique pointer there and there can only exist one unique pointer. So, and we can't copy it.
So like the second line here is the problem, that we assign the P1 to P2.
Yes. So the next code is quite similar, but now we're using a shared pointer. Okay. Then let's look at the results. And most of you voted for that it just prints 42 without any memory errors. And this is the correct answer because now we can copy the shared pointer and at the end of the main, because it's a shared pointer, it automatically gets destructed. So, yeah.
So do you have a more difficult question?
Yes, so this one is the tricky one. Again, quite similar, but this time maybe look at how we initialize P2.
So we call P1.get. What does this function do?
Yeah, I think they touched on it in the lecture last time, but the get function just returns the pointer this smart pointer holds.
But yeah, they said in the lecture, smart pointers, nothing can happen, so it must be fine.
It's really close. Okay, let's look at the results. So, yeah, it was quite close between those answers. And the correct one is the double free. Why? Because at the point where we get the pointer out of the smart pointer or the shared pointer in this case can't know how many instances of shared pointer still reference that pointer. And if we now pass this pointer to a new shared pointer, both of them would just think they are the only shared pointer holding this object, and then both of them would free it at the end. So yes, when you retrieve the pointer from a smart pointer, you should be careful. Okay.
Is that clear to you?
I mean, we still talk about smart pointers.
Yeah.
We still have a recap. So let's look at the leaderboard. Yes, and Tony won, so congratulations.
42 seconds, so this is impressive in comparison to all others. Very nice. Okay, then as you said, there is a recap about smart pointers, so just to go through it one more time. What is a smart pointer and what are the different types of smart pointers that were discussed in the lecture? So in general, a smart pointer does the memory management for us. So what this means is we do not have to free the pointer at the very end because the shared pointer or the smart pointer, whichever type we're using, does it for us. Yeah, so this is quite convenient. But we will also see today an example where this does not work. So it's not smart pointer and it works. We still have to think a bit. In general, inside of the smart pointer class, there is an ordinary raw pointer, so a classical pointer from C, and we just have some functionality wrapped around it. We saw already in the quiz the unique pointer with the property that exactly one such instance can exist to a pointer, which means we cannot copy a unique pointer. So there cannot exist two unique pointers pointing to the same raw pointer, unless we do this kind of stuff what we've seen in the last quiz question, which we shouldn't do. Then there is the shared pointer, and here really the goal is that multiple instances of the shared pointer can have access to the same raw pointer, and that's why we can copy the pointer, copy it to functions, for example, and use it from different places. And there is the third kind of pointer, this weak pointer, with the difference that it does not own the pointer, and this means that it does not think about the memory management. It just says, okay, this pointer exists, but it wouldn't free it. So now the question is, why should we use it? We will see this in the example, but maybe just go a bit more about shared pointers and weak pointers. So we already said shared pointers have multiple shared pointers to the same object. And what do they use internally? They have a reference count. So whenever a new shared pointer instance is created to the same object, the reference count is increased by 1. And this is always increased. And when we destruct a shared pointer, then the reference count to this pointer is decreased by 1. At some point, this reference count will be 0. Then we know we were the last shared pointer, and now we have to free the pointer. And that's the behavior why the shared pointer works. That's what I said. If the last pointer is destroyed, then this reference count becomes 0, and the object will be deleted. So what is the weak pointer? So the weak pointer, I already said, it does not own the raw pointer behind it. So it's basically a shared pointer without ownership. So we cannot access the pointer behind the weak pointer directly. Because we just say there exists this pointer, but we cannot do anything with it. We do not even know whether the pointer is valid or if it was freed. We just know there exists a pointer. And now the important thing is we can take a weak pointer, convert it to a shared pointer using the lock method on the weak pointer. And then if the pointer exists, then we have an ordinary shared pointer that we can use to modify it. However, if the pointer behind it does not exist anymore, then this lock method would fail or would return some error value here. And only if it works, we have the shared pointer, and with the shared pointer, we can have access to our real pointer behind it. Okay. Now, this is, I think, a bit abstract. So we have now the example on it, why we need to use this concept, why it's not enough to just have shared pointers for everything. Okay. This is then your part.
Yes. So as we mentioned before, we now want a bit of an interesting example where we can demonstrate those things. So we want two classes which both hold a pointer to the other class. And we want this to be shared pointers, of course. So this is also why we forward declared the class player here, because here in the game, we want to hold a shared pointer to the player.
I'm sorry, as always.
And in the player, we want to hold a shared pointer to the game, like this. Okay, and maybe we'll figure this now out if this causes any problems. So in the main, we'll create both. One for the player. Oops. We just create a new player, and then a shared pointer for the game. And now I'll use the make shared method. And in the constructor of the game, I want to pass the player. So I want to implement this, of course.
Maybe I can ask something. What is the difference now between this new player and the make shared here?
Yes, so I think it basically the same. So it makes not really a difference because here we are creating a new player, storing the pointer, and this is what make shared does for us. It constructs, it's maybe more explicit because here we never need to touch any pointer or heap allocation. So I would prefer this one here. Okay, then let's implement the constructor. And we need to take the shared pointer to the, this is correct. Shared pointer to the player, and then we initialize our player shared pointer. So this is what we are doing down here. We are passing the shared pointer to the game, and the game stores this player. Now we also need to store the game pointer in the player, and we can't do this in the constructor because we construct the player before. So maybe initialize the game with a null pointer first, and then we'll write some method where we can set this shared pointer to the actual game. I'll call this join game. We take the shared pointer to the game, and then set our shared pointer we have in the player to the shared pointer of the game. And we can call this down here now. So we have player and pass the game. Okay, then maybe let's execute this and see if this works. Yeah. Okay, so nothing went wrong. So, or maybe it just executed, but let's look with Valgrind maybe. Okay, but now we see we have some heap usage at exit. So the pointer didn't actually deallocated themselves at the end of the program. And this is now a bit weird maybe because we used shared pointers. Why didn't this work? Maybe we can go step by step through this and just count how many references this shared pointer hold. So right here, we're creating a new player and a shared pointer to it. So, oops. So the player has one reference here. Then here we are creating the game, but we are also copying the shared pointer to the game. So now the reference count of the player is 2 because the game holds the player, and here in the main we hold the player, and the game is 1. And now down here, when we copy the shared pointer of the game to the player, the same thing happens. We still have 2 player references, one in the main and one here in the game. So up here we have a shared pointer to the player, and here we have a shared pointer to the player. And in the player we have a shared pointer to the game, and in the main we have a shared pointer to the game. So both of them are 2. Okay, so what happens now when we call return 0 here in the main? Well, this shared pointer gets deleted. The reference count of player goes from 2 to 1. Okay, so we have from 2 to 1. This is not 0, so we don't destroy the player yet. Then, okay, the game shared pointer is destructed. The reference count is decreased by 1. But there still exists a player, because it wasn't destructed, that holds a reference to the game. And both have now still have one reference, namely to each other. So nowhere in the program we can actually access this memory, because we can't access the game and we can't access the player, but they still hold each other. So they still count as one reference, and therefore they are not destructed. Yeah. Are there any questions to why this happened? Yes?
Yeah, so when I destroy the game object and there is a shared pointer in it to the player, what happens then to this shared pointer?
Yes. So
So it just disappears, so it doesn't like cascade.
no, when we actually call the destructor of the game here, then the destructor of the shared pointer is also called. So the reference count to this player decreases by 1. But the thing is, the game is never really destructed. We only destruct the shared pointer of the game, but the game is still held by this player here and therefore not destructed.
Yeah, that's really tricky. Just think about whether we can really draw it.
I mean, I guess we could.
Yeah, but should
we do it?
yeah, so this is bonus material then for those which are here. Maybe you can switch on the light. Okay, so we have those 2 game pointers, and now when we destruct this game pointer, right? Okay. So this gets destructed, and we still have this game pointer to the game. Yeah, so this game pointer still holds the game. Now I need to draw the same situation for the player. So imagine that this is the same for the player here. So, no, I need to do it the other way around. So in the main, we destruct 1 player. But we never destruct the game and the player itself, because we just destructed the shared pointers.
Maybe.
You can have this one, this is a bit better.
Maybe if we draw it like this, that if we have the main down here, and the game here, and the player here. So, I don't know, player, the game, and the main. Then we construct a shared pointer to the game, a shared pointer to the player. The game gets a shared pointer to the player, and the player then, with this method, gets a shared pointer to the game. And only when there are no more arrows to one of these objects, then it gets destructed. But what happens at the end of the main is that this one and this one is destructed, but these two do still exist. We have no way of accessing them because all our pointers to the player and the game, we lost them at the end of the main, but they still reference each other and therefore they are not destructed. And that's our memory leak.
I think your explanation was better than mine. Did it become a bit clearer to you? Is someone still completely confused? It's no problem. It's a bit hard to get that, really. Okay. So you can switch off the light again. And
yes,
now we want to have the solution.
Yes.
But isn't this redundant data management because you save the player at the game and the game is the player?
Yes. So the question was, isn't this redundant because we save the player in the game and the game in the player? And yes, maybe there of course are ways where we don't need to use this, and we can think of building this up that we only ever access the game from the player or the other way around. But maybe we want to do something like this, and now this doesn't work.
Okay, then let's see what the solution is. And now the weak pointer is the solution here. And I think we changed which to the weak pointer? The game. Yeah, so we do the following. We take the player now and substitute the shared pointer in the player with a weak pointer. So we use a weak pointer instead. Now we cannot initialize it with null, but we can just leave it empty, so the weak pointer doesn't know about any pointer yet. And we do not need to change anything now. Everything works the same, but we have now a weak pointer here instead of the shared pointer. And remember, the weak pointer does not have an ownership. So what happens then? When we initialize the player at the very beginning, the reference count is 1 because we have the shared pointer. Then we put the player into the game. Okay, so we still have this shared pointer to the game. We have this pointer to the player, and we have the shared pointer in the game to the player. So nothing changed. We really have 2 references of player and 1 of game. But now, when the player joins the game, then we just initialize the weak pointer here, which means the reference count does not increase, and we still have only 1 reference to the game, because it's a weak pointer. And then, when we free now our pointers, so maybe we start with the player, so the player gets, the shared point of the player gets destructed. This implies the reference count of the player is 2, and the reference count of game is 1. Is 1,
Yes.
and game is 1. When the game is now, the shared pointer to the game is now destructed, then the reference count of game gets lowered by 1, so this is 0, which means there is no shared pointer to the game anymore. We need to destruct the game itself. So we call the destructor to game, and this implies that the shared pointer to the player is destructed, which means we get also here the reference count 0, and the player gets destructed as well, and we do not have any memory leaks at the very end. Now we can also try it.
Did you build?
Yeah, I need to compile first, and then call Valgrind, and now we do not have any memory errors left. So this really is the solution to this problem.
So it's like with our drawing, removing 1 arrow between the game and the player. So now this arrow only goes in 1 direction.
So basically remove this error here.
Yes. And now only 1 arrow points to the game. And if we remove that arrow, the game is destructed, which removes the arrow to the player, and the player is destructed.
Okay, maybe we can now try to access the weak pointer as well. Maybe you want to start, and
Yeah.
I will finish up maybe.
Okay, so now I want to continue and implement more logic. So maybe in this game here, I would just want to have a method which returns a string, maybe something like get game info, and we just return some string. Something like this. Okay. And I want to call this from the player. Now, maybe you can already see that we have a weak pointer here. How do we access it? Let's try it. Maybe just do some print state method, where we just print player1. And then we want to call the get game info of the game. So maybe just something like this, and then get game info. Yeah, but because this is a weak pointer, we can't dereference it and access its contents like with the shared pointer.
Okay, so what do we need to do? As we saw in the recap, we need to get a shared pointer from the weak pointer. So we just create here a new instance of the shared pointer to game. And we obtain it by taking the weak pointer and do the lock method on it. And from this moment on, we have now a shared pointer to the game. And now, with this shared pointer, we can, of course, call the methods, because now we really own the pointer. Also, the reference count increased, and now we can use all the methods. Now, what is the difference to before? Of course, if we leave this function here, then this shared pointer gets destructed again, and we're still left with the weak pointer only. So we do not have the problem that from before, that we have shared pointers pointing to each other, because only in this function or in this part of the function there exists a second shared pointer, and once the function is completed, this shared pointer gets destructed, and we're just left with the weak pointer.
So we are momentarily creating an arrow from the player to the game, and then at the end of this function, this arrow gets removed again, so that when we lose our reference to the game, the player also gets distracted.
I think that was the example about that. Do you have some questions about it?
Okay. Then let's continue implementing our own shared pointer. So I already prepared something, namely this class shared int pointer. And as the name states, we now want to implement such a shared pointer on our own. And this should just hold an integer. Maybe the rough idea is just that we have a pointer to an integer, and then also maybe have a pointer to the reference count. And then when the shared int pointer object gets copied, we increase the reference count. And when it gets distracted, one of them, we decrease reference count. And because all of these objects should now hold a pointer to the same reference count and to the same int pointer, we can keep track of this. Maybe this is a bit like a shallow copy, but now we are intentionally using this to create such a shared pointer. Yes. Does now anyone have an idea with what we could need to create such a shared pointer?
So in particular, the member variables.
Yeah,
now,
maybe the member variables, but maybe you also need some, methods. So we need a destructor to update the reference count. Maybe something. Any other ideas? Yes?
Constructor and operator equals.
So, yes, the assignment operator. And if we have an assignment operator, we also need a copy constructor. And we need to think about this later, but when we have an assignment operator, we of course also need to update our reference count in some way. And maybe, most obvious, we need an actual pointer to the heap, which we are representing, and a pointer to the reference count. We can't just store this reference count in this class without a pointer, because we want to share these reference counts between all instances which reference the same heap pointer. Then, maybe start with the constructor. So we have this shared heap pointer. And just like with the pointer from the standard library, we take the heap pointer as an argument. And then when we construct a new heap pointer, we also want to create a new reference count. And at the beginning, we want to set this to 1. Because we have one reference to our shared pointer, which is this one, which we are currently creating. Now maybe let's look at the destructor. Shared, where things get a bit more interesting. So maybe does anyone have an idea what we need to do in the destructor to make sure that we are deleting this integer on the heap when the last shared int pointer is destructed? I mean, we could do it with a static, but a static would mean that we only can ever have one shared int pointer. So, but there could be a case where we have several ints on the heap and all of them can be shared pointer. Yes? Exactly. What we need to do, we start this reference count, and now we need to check if it is 0. So if no object is referencing this one, then we want to actually delete this integer, this one. But first, we also need to decrease the reference count by 1. Because we are destructuring this shared int pointer, this instance of it. So maybe we have 5 shared int pointer objects currently. All of them point to the same heap pointer. We have a ref count of 5. And if we now delete one of them, we want to decrease the reference count by 1. But because there are still 4 other references, we don't want to do anything else. But if we delete the last shared int pointer, so the reference count is 1, we decrease it by 1, and it becomes 0, then we want to actually free our memory. So we want to free our heap pointer and also free our reference count, because you also stored that on the heap.
Maybe we can try it out a bit.
Yeah, let's test it. So let's create a shared int pointer with 10. Create a second shared int pointer p2. And now we would expect that both of those...
you probably want to pass the pointer.
I need to pass the pointer, yes. Yeah, and now we would expect that both of those pointers should be deleted at the end of the main. Let's try this out. Own smart pointer. Okay, yeah, nothing happens here. Maybe let's try with Valgrind. And yes, 0 bytes in use at exit, so everything seems fine.
Yeah, but basically you just implemented now a unique pointer because you cannot copy it anyway. So let's now continue really with the shared pointer that we can copy it. And yeah, so we need to write a copy constructor. And what do we get here? Const shared integer pointer other. And now we learned in the last time always that we need to do some deep copy thing, but this is really one of the instances where we need the shallow copy now, because we really would like that our new pointer points to the same heap pointer and also references the same reference count. So we say our heap pointer is the same as the other heap pointer, and our reference count should be the other reference count. Okay, Anything else that we need to do in the copy constructor? Yeah? Yes, exactly. So we need, of course, to add 1 to the reference count because we have now one more instance pointing to the same pointer. Okay, maybe I take down your shared pointer from before and just copy it. So we have now 2 shared pointers pointing to the same integer. And now let's test it again. Okay, this always works, and Valgrind also says 3 allocations, 3 frees, everything is fine. So we implemented now the copy constructor, and then we also said, okay, we need a copy assignment operator. So what was the signature? Shared integer pointer reference, because we would like to chain assignments. Then which operator? The equals operator. Then we are the left side of the assignment, and on the right side there should be a const shared integer pointer other. Okay, just for demonstration, we have A equals B equals C, and B, that's what we are, C is other, and A is the return value of the assignment operator. The first check that we always do in the assignment operator is to check whether we are the same as other, because then we do not need to do an assignment. So we only need to do it if our address is in equals the address of other. Then we do something. And what do we return? We return ourselves after the assignment. So after this part here, so we return a reference to ourselves, return this.
And this is really important to never forget. So you should always check and make sure that the this pointer is not equal to the address of this other element we are assigning to, because yes.
Yeah, we would destroy it.
Yeah.
Also in our example. Okay, and now we basically just need to implement the destructor and the copy constructor here. Because if we assign C to B, then the original shared pointer that was here, the reference count needs to decrease by 1. Because afterwards it will point to C and not to B. So we decrease the reference count. And then we, of course, same as in the destructor, we need to check whether we were the last shared pointer pointing to that element. So I'm just a bit lazy now, I just copied the destructor part here. If our reference count is 0, then we also need to delete the heap pointer and the reference count. And afterwards, we, as the B, are prepared that we can really assign C. So we need to do the copy of both attributes. So we need to copy the heap pointer from the right element and the ref count. And now we are another instance that point also to C, so we also need to increase the reference count.
So what we did here is, because we assigned another shared pointer to this one, we need to decrease the reference count, which we already had, and maybe free it, and then get the pointer which we are assigned to and increase the reference count of that one. And maybe if you look closer, you can see that this is exactly the destructor and then the copy constructor.
Yeah, so here, this is the destructor, and here, this part is exactly the same as this part here.
Yeah. So when you assign our shared in pointer to another shared in pointer, you are destructuring the pointer we had before and then copying the one we want to assign.
Then maybe let's try it out as well. So we make a third pointer now. and then maybe we say P1 equals P3. So we have now, this is really an assignment because P1 existed before, and then we override it with P3. And we can run it. And also here Wellprint says, okay, we have more allocations, but we still have no error, so everything is fine. Okay, now we said, okay, we had this more or less unique pointer, then we have the copy constructor, but it doesn't feel like a pointer at the moment. There's something very characteristic missing of a pointer.
Yeah. So maybe the most important thing that's missing here is that once we have this shared pointer, there's no way we can access our content anymore. And maybe, because it's a pointer, we can now implement the dereference operator, so the star. Well, it should return a reference, because we're dereferencing the pointer. We're implementing the star operator, and maybe if you look now, we don't have any parameters, because we don't want to override multiplication, we just want to dereference our shared in pointer. And yes, that's what we are doing, because we have a reference return value. We dereference our heap pointer, so from this pointer we get a reference and return it. And now in the main, we can do something like this, and dereference this P1 and assign a value to it. Yeah, and maybe also access P3.
So this should also be 2 because P1 and P3 are the same.
Yeah, we could test it.
Mm-hmm.
And yeah. So we assigned a value to P1, and because P1 is equal to P3, when we dereference P3, it's also 1. 2.
Yeah, it's also 2.
2.
Yeah. Okay, I think this was our shared pointer. It most likely will also be part of the homework to some extent. So, are there any questions? Yeah?
Why do we need reference as a return? Why can't we just return an integer?
Yeah, we could return just the integer, but then we can't assign to it. Because then the integer is copied out of the heap into the main, and if you assign to it, nothing happens.
I think it wouldn't even compile. Or does it?
I don't know, it could.
Well, maybe we try it just out.
I think it would.
It would compile.
Yes, but now oh yeah, okay, here it wouldn't compile, yes.
So we could do this, right? Mm-hmm. Because then we just get the copy, but we cannot assign to it. So put back the reference here.
Yeah, we could also return a pointer, but then you would need to dereference it 2 times.
This would be funny.
Yes? This one here, we're just dereferencing ref count, so to get the value from ref count, and then this minus, like we would do it afterwards, we could do it here too. So it's just decreasing it by 1, like this. Why do we need to decrease this by 1? Yeah, because we have here these 2 objects shared int pointer. These are 2 different objects on the stack, and they both more or less point to the same pointer on the heap. And when we destruct now one of them, we don't want to free the memory because we still hold a pointer to that memory. And we don't want that to get invalid. We only want to free the memory once we don't have any reference to this memory anymore. And that's why we need to decrease the reference count, because we somehow need to keep track of how many shared pointer exists to this heap location. So we can make sure that when you're really deleting it, that we have no reference to that location anymore.
Maybe I can also rephrase it if we just go through the HBB file. So when you initialize the first pointer, then the reference count is 1. When you do a copy of it, then the reference count becomes 2. And when you destruct then one of those, then the reference count gets decreased by 1 so that it is 1. And when the second one is destructed, then the reference count becomes 0, and then we just delete the pointers.
Yes. Yeah. It seems complicating, or it could seem complicated. But yeah, if you maybe just try it out or go over it one more time, I think it could be, once you get it, it's not that hard. Let's phrase it like that. Okay.
Then I think we move on, right? Mm-hmm. Okay. Okay, now we come to something completely different, which are algorithms and lambda functions, which is really something new to you now. This is not discussed in the lecture. And yeah, we think it's interesting and you should know it, and we can do really nice things with that.
Yes, and most programming language can support a concept similar to this one.
And I think everyone who attended VSP also saw lambda functions in Python from us.
Yeah, but they're a bit different in C++.
You said it's not in the lecture. Can this come to the exam?
No.
Okay. Yeah, but it's in the homework. Yeah.
So we do this homework about some funny topics. Mm-hmm. Yeah. Okay, what is the motivation? Why would we discuss this? So C++ offers a wide range of algorithms which are already implemented. For example, this includes sorting or finding an element or do some transformations. I think find, we have seen this in the standard map, I think, at some point. And yeah, these are usually used together with some container, so a map, a vector, a list, whatever. And we will focus on the standard vector. And we will use these algorithms on a vector and together with an iterator. We've seen this last time in the practicals. An iterator is more or less a pointer to an element inside of a vector or some other data structure. And yeah, some parts of the algorithms need to be customized. Yeah? If you think about sorting, then sorting is a procedure, but we need to know how they should be sorted. Should they be sorted in increasing order, in decreasing order, in any other order that you can imagine? So we need to specify some parts of the functions of the algorithms.
Yes, and if you, for example, have a more complicated data type, like an ingredient for a recipe or something, then we need to know what we should sort by, maybe the name or maybe how much there is in the recipe. So this could get, as complicated as you want it to be.
And yeah, we usually do this by passing then a function to the algorithm, and that's a good way or a good point then to introduce lambda functions, and we will come to this in a second. And what the interesting thing about this, we will now iterate over vectors, we will modify them, but we will never use a for loop or any kind of loop. We will just use functions, and we will never use a loop now in our program. Okay, so let's see what we have prepared. This is here. I need to open the other one as well. Okay, so this is the only for loop that we will see, but we can delete it in a few minutes. So we have a vector of ingredients, and each ingredient has a name. Yeah, we see this also here. And then we have a unit, so which kind of unit we are using here. And then we also have an integer, no, we have a double for the amount, how much we need of this ingredient. And then we just have some basic functions here, which is the constructors, some getters and setters, and just ingredient method that multiplies the amount by some factor, so we can double the ingredients, for example, and also an output operator here that we can easily print an ingredient. As you can see here, we can just call cout with an ingredient I, and this does the output job. And yeah, we have this operator here, but it doesn't matter. Okay, yeah, and I just execute the program, and then just to see the output once. So we just have the output, okay, everything of our vector is printed. Yeah.
Okay. Then maybe let's start with one of the algorithms, which is probably the easiest or the simplest one. Yes, we are often writing loops like this. So we have this for loop. We take one element out of some container, maybe a vector, and then doing something with it. Oops. But how could we implement this as a function? So we know that if we have something we are doing very often, we often want to implement this in a function so we can reuse it. But how would we do this with a for loop? Does anyone have an idea? Yes.
We could have a function that takes an iterator to thing,
Mm-hmm.
and then gets the lambda and executes it on every.
Mm-hmm. Okay, so the idea was we could create a function which takes an iterator and then executes some other function that we specify on every element. And yeah, this is how we want to do it. And maybe I'll show this with this bit more extensive example. So when we iterate over some container, we always take the iterator to the beginning, then increase the iterator as long as we are not at the end. Yeah, and then take the current in the loop, take the current element of the iterator and apply something to this. And I call this just now the body function. But what we're doing here would be the same as what we are doing in this for loop. So more or less we are abstracting away what we are doing in the loop. And now there is this standard for each function, which also takes an iterator to the beginning, an iterator to the end, because like here we needed to know how long we should iterate, and then one function which it calls for every element. Oops. Okay, maybe let's implement this, or maybe replace this for loop with this function. So what we would...
Well, sorry. Yeah.
So what we would do, instead of iterating like this over the ingredients, is call the for each function from the algorithm's header. Pass the beginning and the end iterator, and then some function. Well, we need some function, so maybe let's implement it. And here we just take a const ingredient, a reference to it, so we don't need to copy it. Print it, And let's put this here now. So we have our print ingredient function. Oops. So what this is doing is like up here in this loop, for each iteration in here, we're calling our print ingredient function with the current element. And this up here is the same thing this for each function does down here. It iterates over these iterators and calls this function for every element. And yeah, we implemented the function up here.
So this is already really nice because now we cleaned up our main function a bit, because just instead of writing 4 lines of code, it's just a one-liner, basically, this for each here. But with the cost that we, of course, need to write this print ingredient here. So we need to specify this function somewhere else. And it would be really nice if we could specify this function directly as a parameter here in the for each, or above as a variable, instead of that the function is somewhere up here. So is there a possibility to do this? And the answer is yes. And now this is the lambda function. So what is a lambda function? It's an anonymous function in the sense that it does not, that it's not visible here as really as a function, but it will be stored then as a local variable inside of the main, for example, here. And this is the syntax of the lambda function. So it looks really a bit odd. So we have here some squared brackets, then some round brackets, specifications, an error, and then the body. We will not discuss everything today. We will skip the captures, we will skip the specifications, we just focus on the parameters, the return type, and the body of the function. And yeah, so we have this print ingredient function from before, and now we would like to have this lambda function. So the syntax was, we have these squared brackets, we ignore them, we just need to write them. Then we have a parameter, okay, this is the constant ingredient, same as in the print ingredient. Then the return type is now with this error on the right-hand side, so this corresponds to this void here. And then we have the function body here as usual. And this function is then stored in this variable, which is called print ingredient lambda, with, we will usually use now auto as a data type, because the real data type for lambda function is rather complex, so we'll just skip it by writing auto here. Okay, now I am lazy, I just copy my function. And now I have my first lambda function here. And yeah, what can I do with it? I first would like to demonstrate it with the for loop. I don't know the hotkey now. Toggle line command. I can use it as an ordinary function. So I can also call now print ingredient lambda on it in this for loop. So if we try it out, Python, okay. So we run it, print it. So the only thing that is printing is this for loop here. So really this printing works. And of course, we can really get now rid of the loop. We can specify this function also directly here in the print ingredient lambda. So this is now the function that should be executed for each element in the for each. And also this time it works. And if we like to do so, we can also write the function directly here. So I can maybe copy this part and put it here. And I don't need this guy anymore. And now I have my function implemented as a parameter in the for each. Yeah, let's run it. Yeah, I don't need this function anymore, but it doesn't matter. And also now we can execute it and this works. And now it's more or less a one-liner or for each loop. And maybe it also gets a bit clearer now where we would say this is an anonymous function because now it just exists here as a parameter, but we can never call it from somewhere else.
Yeah.
Okay.
Yeah, so this is really cool because now we can pass functions to other functions and do cool stuff like this. Yes, so maybe just for each loop, yeah, it's nice, but one could argue it's still longer than writing a normal for each loop. So let's look at something more interesting, which we could do with these lambda functions. Namely, we have this standard transform. In other languages, it's also sometimes called map, even though that's a little bit different.
But it doesn't have anything to do with a really map that we've seen in C++.
And similar to the for each function, it applies a function to each element of the container. But now this function that it applies to each element can now return a value which is stored in a new container. So for example, you could turn one vector into another one by calling transform on it. Yeah, and here's an example. So we call transform here, pass the begin iterator, the end iterator, and then from some other vector also the begin iterator, because it needs to know where to store these transformed elements from this original vector. And then, of course, our lambda function, which specifies what we want to do. So, yeah, let's try this out. Yeah, so it takes one argument and returns a new value. Yeah, maybe I'll do it. I'll comment this out and do it up here so we can see what we are doing. Yes, so the first thing we need to do, because we are storing into a new container, is we need to create one. So let's create a vector of ingredients. Maybe we want to adjust each ingredient, so let's call it adjusted ingredient, the end. And we want it to have the same size. And with vectors, if we can pass to their constructor as the first argument the size it should take. Okay, now let's try transform. We pass the ingredients.begin, the ingredients end. So this is the vector we iterate over where we take our elements from. And now, with the adjusted ingredients, we'll pass the begin vector. So it will iterate over these iterators, apply a function to each element, and store the result into this vector. Now we also need to specify some lambda function. And this again, maybe I'll put this in a new line. Yeah, something like this. So I'll create a lambda function here. This lambda function takes one ingredient. And now it also returns a new ingredient. And what we will do is we adjust the ingredient, by just multiplying it by 2. We can take a quick look at this function. Adjust ingredient really returns a new ingredient with the adjusted amount. So it doesn't modify this ingredient here. It returns a new one. So this is what we want to have. This is what we want. Yes, so this works. And now down here, we also need to change this vector because we want to print the new adjusted ingredient vector. And yes, this worked because we have 10 here, and now here we have 20.
Very nice.
Yeah. but it's still a little bit weird because we would always need to create a new vector if we just want to transform it in some way. And yeah, luckily there's a solution because we can call this transform method with the third argument being the same as the one we are transforming. So now it really transforms this vector. We iterate over this one and store the result in this one, which is the same. So we take one element of the vector, transform it with this function, and save it back into the same vector. We can also try this. Yes?
What would happen if the adjusted ingredient is smaller than the ingredient?
Yeah, then we would, so the question was what would happen if the adjusted ingredient is smaller than the ingredients, and most likely I think we would get a crash at runtime because we're accessing memory out of bounds. Yeah, so let's pass the ingredients vectors 2 times here. First to iterate over, and second to store it in. I need to update this one too. Yeah, and now we're taking one element, adjusting it, and storing it back into the same vector. Let's try it, and we get the same output, even though we are printing the old vector. Yeah, so this worked.
Then we have another algorithm, which is the remove if algorithm, and in other programming languages it's often called filter. So what does it do? It removes elements from a container that fulfill some condition. And yeah, as we did this also with the last 2 algorithms, this condition is then passed as a lambda function. And yeah, this is the function again, remove if. We specify the begin and the end, and then the condition as well, that we, yeah, the condition where we need to remove elements. So we just continue with our vector from before, and maybe we would like to live healthy and we would like to skip the sugar. So we'll remove all elements that have as the name sugar. So we have std remove if, then we have the range of the vector, and then we need again the lambda function, ingredient, what is the return value? This should be now a Boolean. If it should be removed, then it should be true, otherwise false. And we can just check, or we can just return, is I.name the same as sugar? And if I get name as sugar, then remove, it gets removed. Okay?
You didn't save?
I didn't save, thank you. Now we can run it, and there is still 5 ingredients on our list, but we removed the sugar.
And apparently the last one doesn't have any name.
A special ingredient here. Now, this is of course intentional. So the remove if function does not resize the container. So it just shifts the elements around, that the first elements are the correct ones, and everything that should be removed is at the very end of the vector. And we have to manually resize the container and remove those garbage elements at the end. And for this we use now not an algorithm, but a function of the vector, which we haven't seen so far, is the erase function. And it takes just 2 iterators and erases all elements from the from iterator to the to iterator. And this really resizes the container, then this really deletes the elements. The remove if does not resize the container. And yeah, why should we know how many elements do we need to remove? And this remove if function returns an iterator to the new end of the container. So in our example, we would get, as we deleted one ingredient, we would get an iterator to this element. And we need to delete everything until the end. So our to iterator would be then vector.end. So implement this here as well. So the remove if returns now an iterator. Yeah, the type is a bit difficult, so we just write auto here. And then we call on our vector the erase method, and we want to erase everything from this iterator to the end of the vector. And if we give it now another try, then we really have only 4 elements in our list again. Okay, we have 2 more algorithms, but they are really fast now, I think.
Okay, so we have the sort, and as the name says, it just sorts an element within the container. But if these elements are not primitive type, so if they're not integer or double, but maybe something more complex, how do we compare them? And there are 2 options. Either we specify a lambda function, like I think we already said a few slides ago, which just compares these 2, or we implement this less than operator with our types that are in this vector we are sorting, and then we can just omit this lambda function, and it will use this operator. Maybe we can try out both now. So we can say sort, then the ingredients, the beginning, the ingredients, the end, and then we'll specify a lambda function. I'm a bit lazy. So like this, which takes 2 ingredients and returns a boolean if the first one is smaller than the second one. And what I want to do now is sort them by their name. So I'll get the name from the first one and get the name of the second one and compare them like this. So the string has this operator overloaded. The name is an std string, so we can do this. And we have our lambda function, which compares now 2 elements. Oops. And if you run this now, you can see they are sorted. Okay, but what if in our ingredient we already implemented the less than operator? Yes, we already did this. So we implemented this less than operator, which does the same thing. It just compares the names. And because we did this, we can also just omit this lambda function, which does the comparison, and let C++ automatically call our less than operator. And we see it's the same result.
Okay. And then we have one last function that we would like to show you, which is, yeah?
No, it really is like string compare in C. So it compares the whole string, one after the other. So if the first one are the same, it compares the second one and so on.
Like in a dictionary.
Yeah.
And the last function that we would like to show is unique. So maybe let's show it here. So we have now 2 times the ledgers on our ingredients list, and we would like to see these now as duplicates. Of course, the unit is now different, but we'll just focus on the name now. And we would like to eliminate all duplicates in our list. And yeah, we can achieve this with unique. The important precondition is that the duplicates must be next to each other. So if we would apply this unique function here, then it would not find out that we have the ledgers twice. It really needs to be sorted like here at the end. And then it removes all duplicates from a container. And it's very simple. We just need to specify unique, vector begin, vector end, and yeah, some lambda function again for the comparison, which I probably forgot, because we need to specify when two values are the same. So like in sorting, we have this less than, and in the unique, we need to implement an equals equals operator. Okay, then let's try it out. After the sorting, we call unique, ingredients begin, ingredients end, and then our lambda function, which takes two ingredients, I1 and I2, returns again a Boolean.
If they are equal.
And we say they are equal if their names are the same. For simplification now. Okay, then let's try it out. And yeah, same thing as in remove if. Unique also does not resize the container. It also keeps the same length, and everything which was removed at the very end is then garbage. So also in this case, we must obtain the iterator as the return value from unique and call the erase method on the vector from the second, from this iterator that unique returns to the very end. And if you run it now, we really remove the second ledges and we're just left with our three ingredients. And I think I just have it on the slide here as well. So these algorithms really do not change the size of the container, but they just move the elements around if necessary. And if you remove something, then you really need to decrease the size of the container at the later point.
Because, yes?
But the values, if we go to the example, I missed now some value because we had 4 units of letters and 2.
Yeah.
So I'm losing information if I don't do this correctly, right?
Yes, because we just did the comparison on the name. And we said, okay, if the names match, then they are the same.
Yeah.
We could, of course, now implement something that says, okay, we do not only compare the names, but if the names are the same, then we put the units of the second element into the units of the first element. I think you wanted to say something.
Yeah. So we always need to erase this because these algorithm functions only get the iterator to the beginning and to the end. And because they act like pointers more or less, they can't resize our container with that. So yeah, therefore we need to erase it manually.
And they basically do not know which container we are passing to the function because they behave the same for all different type of containers.
Yeah, and for each container, it could be different logic which resizes them.
Any further questions? Yeah?
So what I didn't quite get is why do those algorithms need to be assigned to an iterator? Why do I have to say also iterator equals?
So usually you do not need to do this. For example, here, sorting, this is done. Yeah? You're done with that. But if you remove elements from the container, for example, because you remove duplicates, or you filter them based on some condition, then you get, as the result, an iterator to the new end of the vector. Because if you have 10 elements and remove 4 elements, the vector still has 10 elements after the algorithm, but only the first 6 are valid. And the remaining 4 elements are not valid because these more or less are the elements that you removed. And then you get an iterator to the first invalid element. And from this invalid element until the end of the vector, you have to manually erase the elements then, because an algorithm cannot change the size of the container. Yeah? yeah, these are types of
Yeah.
containers.
Anything you can get an iterator of. Okay.
I think we're done then. When does the lecture start? In 4 minutes the lecture starts, so very short break now.
Let's say 5.
Okay, in 5 minutes. Then thank you and see you next week for the last practicals.